Hey there, my name is Chadin, and I'm the suspension lead at BMS. I'm glad that you all chose to join Viking Motorsports, and I hope you have fun here by building new skills and using the skills that you've already learned in your classes. So, what is suspension? Suspension basically connects the tires to the frame of the car. This is done through many suspension components, such as control arms, uprights, spring and dampers, wheel centers, and many more. Our main job is to make sure that the tire has the most amount of grip on the track, mainly during cornering, because when you make a turn, the inner tires have the tendency to lift off the ground. We make sure that this doesn't happen by analyzing tire data under different alignments that includes angles such as camber and toe angles, damper tuning, control arm distances, analyzing tire data, and many more. To achieve this, we set up a suspension design goal, which is to maximize the cornering speed and stability of the car through accurate simulation of the car's behavior. Then we divided suspension into three subdivisions: outward suspension, responsible for uprights and hubs, wheel centers and brakes; kinematics, responsible for wheel loads, tire data analysis, and a kinematics and suspension modeler. And then we have dynamics, responsible for spring and damper tuning, steering rack, and a vehicle and track simulation. This year, we're going with a double wishbone suspension setup, which means that we have an upper and lower control arm, or as some people call them, A-arms. We've done this design in the past and in our previous car. The reason why we go with a double control arm suspension is because it allows us to really control how the wheel behaves whenever we're cornering or going over bumps. We do this by playing around with some parameters, such as camber angle, which is how much the top of the tire points inwards or outwards of the car. This helps the car with cornering stability. Or we can mess around with toe angle, which is how much the front of the tire points inwards or outwards of the car. This helps with straight line stability. We can also play around with caster angle, which is the angle between the lower ball joint and the upper ball joint. This allows the wheel and steering wheel to self-center itself. In terms of FSAE rules, suspension doesn't have as many restrictions as chassis and electronics do. Most of our rules and restrictions cater towards how we mount our suspension components, but there are some specific ones that I'll get to later on. Let's start with control arms. We work very closely with the chassis subsystem so that we can work together on its mounting points. So far, we've mapped out these control arms using a bunch of chassis constraints, equations, and mounting points. And then we found out the instantaneous centers to get their shapes right. Next, we have the uprights, which is the silver portion. This attaches the wheel to the hub, toe arm, upper and lower control arms, and the brake package, which includes the brake caliper and rotor. So far, this model has slots for the upper and lower control arms. So the upper control arm slot would be right there, and the lower control arm slot would be down there. And it also has an integrated toe arm slot. We also have a brake caliper mount, which is right here. This is one of those difficult parts about an upright design, both in the past and still present today. It's hard to design something this complex while still keeping in mind that it needs to be manufactured easily, which is the issue with the brake caliper that the manufacturing subsystem will tell you more about. Next, we have the wheel hubs, which is this tan portion right here. The wheel hub assembly is made out of the wheel hub, the rotor hat, and also the alignment dowels. The wheels bolt right onto it and allows them to rotate freely. The whole wheel hub assembly slides right into the center of the upright, where it's separated by a bearing. In terms of rules, we need to incorporate a device such that if a nut were to come loose, it wouldn't come loose all the way. Our solution to this is to use a safety wire. Safety wiring is when you attach 2 or more nuts with a wire. And when this nut starts to come loose, it'll tighten the attached nut, preventing this nut from becoming loose all the way. This year, we're going with center locking wheels, which we designed a hub around. So far, we have the basic geometry that models the hub, the rotor hat that mounts onto the brake rotor, and then the alignment dowels to align them when you're taking the wheels on and off. Next, we have the wheel center. In the past, we've gotten them off the shelf, but this year, we're trying to manufacture them. We actually held a design competition earlier this year where the team got to vote on a winner, and this was the winning design. It's a pretty good looking wheel center. A difficulty that we had was designing this around it being manufacturable. That meant taking away some chamfers and fillets, thickening up some thin members, and rounding off some sharp corners. In terms of rules, the wheels have to be 8 inches or more in diameter. Our wheel shell, which is this silver portion, is 10 inches, so we meet this rule. We had plans for an anti-roll bar this year, but due to some delay in design work, we decided to save it for the next car. There's a lot of research that's been done towards it and also a SolidWorks model to supplement it for the next year's car. Next, we have the steering system, which is made out of a steering rack that translates the steering wheel motion to the tires. It also has a steering shaft that connects the steering wheel to the steering rack itself, and then a tow arm that connects from the steering rack to the wheel. This year, we're reusing a steering rack that we got off the shelf because it's the most cost-effective option at this point. Plus, it's a good and well-working steering rack. FSAE rules-wise, we're required to have a mechanical steering system with no electronics parts, which we do. Suspension also uses MATLAB for analyzing tire data and simulating the car around a track. FSAE has tire data provided by CalSpan that has a ton of tire data from different types of experiments on how the tire behaves. These experiments range from testing different camber angles during cornering, collecting forces on the tire at different tire pressures, how the vertical loads on tires affects its behavior, and many other tests. Our job is to download this data and use MATLAB's provided code for analyzing tire data to get coefficients for a formula that outputs the lateral force on the tire, which is this F of X right here. Analyzing all of this lets us know when the tire is going to slip or lose traction. The hardest part about analyzing tire data is trying to figure out the code. It's pretty complex, and you have to take it one step at a time. So far, we've calculated the coefficients and made graphs for each of these coefficients. But there's still more work to be done because this is one of those projects that's always going to be ongoing. We're always going to need to know how the tire behaves, especially for suspension, since our focus is how the tire behaves. We also do a vehicle and lap simulation on optimum lap. On here, you input your vehicle parameters, make a map, simulate your vehicle, and then you get a bunch of graphs. So far, we have graphs for throttle and speed around each point of the track. You can also get some heat maps that visualizes all that data. Then you can export all this data to a CSV file so that you can open it on MATLAB. Right now, we're simulating our EV in the endurance event, where you drive the vehicle around a track for 16 laps or around 20 minutes. It really tests our car's performance and also the battery, which is why we're focused on how the battery behaves. As of now, we can simulate the average current drawn from the motor, the average current usage needed to survive endurance, and also the battery state of charge, or the percentage of the charge that's left. We also do force calculations on every suspension component to make sure that it can take the loads that are put on it. You don't want your wheel center to snap right when you make a corner because you don't know how much load it can withstand. These calculations are basically free body diagrams and what is taught in a normal dynamics class. They're very important to calculate because they supplement FEA. FEA just shows you where the strain occurs. Hand drawing free body diagrams gets you the actual force values. So far, we have an Excel sheet with calculations of forces on the tire during braking, cornering, and how the mass transfer affects it. But we need to calculate forces on each suspension component. Since validation season is approaching, it's a perfect time to hop on this and do some free body diagrams with me. We also get to choose the springs and dampers for our car. Springs absorb the energy from an applied force, and the dampers dissipate that energy so that the car doesn't oscillate up and down. There aren't any FSAE rules that constrain us. The only rule that we have to follow is that we are required to use a spring and damper system. So far, we have a variety of dampers and springs to choose from. Some cost a lot, and some are very inexpensive. We also have the option to reuse our old ones from our last car. Thanks for listening in on what suspension is up to. Remember to choose a subsystem that you're really interested in. You'll get to know what chassis and electronics do even if you join suspension, so you're not restricted on what you can learn. Thanks. Bye.